Hi everyone, my name is Xieling and I am a PhD student from the Hong Kong University of Science and Technologies. Today I would like to share our paper, TENET, Joint Entity and Relation Linking with Coherence Relaxation. This work is conducted by me and my supervisor, Professor Lei Chen and Dr. Chaorui Zhang from Theory Lab of Huawei Technologies. This is the outline of today's talk. First, I'll briefly introduce the background, problem definition, and motivation of our work. Then I will present the detail of the end-to-end joint entity and relation linking problem. Finally, I will conclude this talk with demonstration of experimental results and a summary. And first of all, I would like to share basic background about knowledge bases. A knowledge base stores a collection of facts in the form of subject, relation, and object triple. A subject can be a real-world entity, and the object can be a real-world entity or literal. And the relation is a predicate which connects both terms in a triple. In this example, the entity John Lennon is the subject, the entity Beatles is the objects, and the predicate member of is the relation holding between them. Knowledge bases are quite popular in nowadays downstream applications, such as entity searching, question answering, and recommendations. Take the traditional question answering task based on KB as an example. Given this query input by the user, we link the John Lennon to be the British singer as entity, and where born to the predicate born in, so that we can target at Liverpool, the city, as the answer to these questions. KB population is the task that takes an incomplete KB and a test corpus as input, then extract knowledge from the test to fill in the incomplete elements in the KB. In this example, our input is a piece of text talking about John Lennon, while the output is a list of triple regarding to John Lennon and Beatles extracted from the text, which can be organized as the ontological knowledge in KB by entity linking and relation linking. To support both the question answering applications and KB population tasks, end-to-end joint entity and relation linking has drawn significant attention in industrial and academic communities. In this problem, the input is a document as well as a target KB, while the output is dimensions extracted from the documents with link concept in the target KB. In the example, given the document, our goal is to output the noun phrases such as Michael Jordan and the link entity Professor M. Jordan, and the relational phrases such as studies and the link predicates film of study. Recent techniques has been proposed to address both entity linking and relation linking tasks jointly or separately. However, most of them ignore the coherence of entities and relations, which is important for the disambiguation and linking. For example, if the noun phrases artificial intelligence refer to the branch of computer science rather than the movie, then we would expect Michael Jordan in the same document to be the computer scientist rather than the basketball player. Therefore, all-link assumption is proposed by some of the existing techniques, which assume that all entities in the documents are densely connected in the KB. These methods build a complete knowledge coherence graph among the entities, and then derive a mass clique or dense subgraph to obtain the best set of entities that preserve the coherence. And we refer to these approaches as all-link. So take these documents as an example, where the optimal candidate entities of Michael Jordan, artificial intelligence, and machine learning are connected to each other, which reflects the all-link assumption. However, in real-world scenario, not all the nouns or relational phrases in the same document are connected to each other. Take this document as an example. Although Michael Jordan, artificial intelligence, and machine learning are closely related to each other, the entity Brooklyn is not related to any other concept in the same document. There is a sparsity analysis conducted in 7 benchmark entity linking datasets in a TKD 2018 paper. The results shows that in most real-world datasets, the entity coherence graph is closer to the tree-like, train-like, or forest-like, rather than a dense graph. Currently, there are 2 works that relax the all-link assumption to the pair-link assumption. Instead of looking for a connected subgraph, the first work, MinTree, formulates the disambiguation task as a minimum spanning tree problem on the knowledge coherence graph. And the second work, EARL, formulates the disambiguation task as a general travel salesman problem. The solutions of both problems relax the all-link assumption, since not every pairs of the nodes are required to be connected in both problem formulations. However, the pair-linked assumption is still not satisfactory. By formulating an MST or GTSP problem to cover all the nodes, we assume that every entity is connected to at least one of other entities. But in real-world scenario, especially the joint entity and relation linking task, there are isolated concepts that are not connected to any other concepts. Take this document as an example. The entity Brooklyn and the predicate travel to is not connected to any other concept in the document. Moreover, many newly emerged noun phrases in fresh articles are non-linkable. It is reported that over 30% of the triples extracted by rework from a benchmark dataset cannot be linked to any Wikipedia entities. To summarize, there are two major technical challenges in this problem. The first challenge is the sparse coherence problem, since the existing solutions cannot detect isolated concepts while preserving partial global coherence. And the second challenge is the end-to-end extraction problem, since it is difficult to capture the coherence with multiple candidate mentions for one phrases. For example, understand the presence of the entity M. Jordan professor should help to determine the correct mention, fellow of the AAAS, as opposed to separating fellow and AAAS into less informative concepts. Next, I'll briefly discuss our proposed solutions to address the end-to-end joint entity and relation linking problem. First, we construct the knowledge coherence graph, which aims to capture the semantic distance among the concepts. An edge connecting a mention and its candidate concept is weighted by a score of local semantic distance, which is the prior matching probability that the concept is the correct linking of the mention. An edge connecting a pair of concepts is weighted by a score of global semantic distance, which is based on the cosine similarity between the embedding of the concepts. We then formulate our problem as an M-rooted coherence tree cover problem. Given a knowledge coherence graph and a set of mention M, an M-rooted coherence tree cover is a set of trees which satisfy the following requirements in our problem. First, a certain set of nodes are included in the final derived graph, and second, not all the nodes are connected. And third, it should preserve the partial global coherence. To satisfy these requirements, we propose the following conditions in our problem. Each tree contains a distinct mention as its roots, and each node appears in at least one tree, and the trees in the tree covers can share nodes and edges. We further set the weights of a tree as the total weight of its edges, while the cost of the tree cover is the maximum weight of its trees. Our goal is to find a minimum cost M-rooted tree cover. This problem is proven to be NP-hard by a reduction to the bin pack problem. Next, I will use a simple example to demonstrate the motivation of these problem formulations. So here is a satisfactory tree cover that meets our goals. So first, in this example, every mention is contained in the final derived tree cover, since each tree is rooted from a mention. This satisfies the requirement that we would not exclude any mention. And second, in this example, there are 3 disjoint trees. This satisfies the requirements to relax the density connection coherence to a sparse coherence assumption, which allows the existence of isolated concepts. We further ensure that the nodes within a small semantic distance to a specified mention MI are connected into a tree TI rooted at MI. In this way, the coherence in each tree TI is guaranteed. By setting the cost of a coherence tree cover as the maximum cost instead of the average cost of the trees, we avoid the domination of some lightweight edges over the other edges. The reason is that a lightweight edges only indicates a small semantic distance between one pair of nodes in the local view, instead of most of the nodes in the global view. For instance, the edges between Michael Jordan and M. Jordan, who is a basketball player, would be much lighter than the edges between Michael Jordan and other candidate entities, since the basketball player one is more popular. If we employ average edge weights as the cost, then some tree covers with the edges may easily dominate the other selections and lead to unsatisfactory results. And to address the M-rooted tree cover problem, we propose an approximation algorithms where the input includes a knowledge coherence graph, a set of mentions, and a bound B on the weight of each tree. And the output is an M-rooted tree cover of course at most 4B. And for each mentioned nodes as roots, we produce a set of related concepts. I'll demonstrate the brief idea of the algorithms using a simple running example. So given the knowledge coherence graph, we first prune the edges of weights larger than B. Hence, every pair of nodes with semantic distance larger than B is disconnected. We then contract all the mentioned nodes in M into a major root node R. Next, we compute a minimum spanning tree on the graph with pruning. Specifically, we apply the Kluskas algorithms, which iteratively takes an edge with the smallest distance into consideration. We do not use the print algorithm since we do not group the MST from a specified root. Then we decompose the major root R back to a set of mentioned nodes and obtain a set of trees. In the next step, we split each trees into a set of subtrees, and the iteration is to constrain the total weight of these subtrees so as to bound the maximum semantic distance between any pair of nodes within a subtree. In this way, we ensure that all the nodes in the subtrees are correlated. And finally, we connect as many subtrees produced in the last step as possible to each mentions, while each connections produce a trees in the final tree cover. Since maximum matching only maps the subtrees to the mentions within distance B, this ensures that the weight of each tree in the final tree cover is also bounded. To summarize, the last two steps guarantee that all the nodes in the tree Ti are correlated to the mentioned nodes Mi. Next, we propose to generate mention groups and canopies. The motivation is to improve the mention selections based on the global context coherence. For example, in the first sentence, knowing the presence of the entity Adam and Lloyd, who is a director, help to deduce the correct mention Mary and Max, which is an Australian movie. On the other hand, in the second sentence, the linguistic and social anthropologies indicates that Mary and Max should refer to two distinct entities. Our goal is to assign the overlapped mentions in one mention group. We illustrate the goal by a simple example. Given the document Michael Jordan is a fellow of the AAAS, we employ pre-specified linguistic features to produce two mention groups. For the second mention groups, we have two distinct canopies. One contains two short text mentions, fellow and AAAS, and the other contains one long mention, fellow of the AAAS. For one mention group, only the mention in one canopies are selected. In other words, we either select fellow and AAAS in the same time, or just select fellow of the AAAS. Our final knowledge disambiguation task is to select an optimal set of mentions which best describe the semantic meaning of the documents, with each of the mentions linked to an optimal concept. So the input is an M-rooted tree cover and a set of mention groups with the related canopies, and our output is a set of mentions with each mention linked to a concept. Here is the major idea. We compute a minimum spanning forest employing the strategy of Kluskas's algorithm on the tree cover by iteratively taking the smallest edges into considerations. We further propose 4 pruning strategies. To summarize, the pruning strategy guarantees that only one concept is selected for one mention, and only one canopy is selected for one mention group. We then briefly present our experimental results. We conduct the experiment on 4 real-world datasets with comparisons to 5 SOTA techniques. We employ different NLP tools to recognize the noun phrases and relational phrases in the given documents. Moreover, to construct the knowledge coherence graph, we index over 91 million entities and predicates in Wikidata as candidates and generate the corresponding embeddings for them. We also conduct a statistical analysis of the percentage of the non-linkable mentions in the documents of all the datasets. As shown in the table, there are a considerable amount of non-linkable noun phrases and relational phrases, especially in the long text datasets such as news, MSNBC19, and TRX42. We further investigate the sparse coherence problem in these datasets based on 2 metrics, the density of the concept in each document and the average degree of the concept in each document. The analysis depicts the sparse coherence of the entities and concepts in both matrices. Specifically, in the long test datasets such as MSN BC19, which contains over 22 entities per document, each entity is only connected to less than 6 other entities, with closer than 0.7 distance averagely. Here is the performance of TENET and SOTA on the joint entity and relation linking task. To summarize, compared with the systems that disambiguate each mention separately, the system that preserve global or partial coherence achieved better performance on F1 score. Our system TENET achieved the best F1 score on all the datasets. Specifically, the performance of all systems on the relation linking task is not as satisfactory as on the entity linking task. There are two major reasons, according to our case study. First, all the systems tend to recognize the phrases representing predicates as entities. And second, some hidden relations are ambiguous and difficult to be identified. Therefore, the precision is affected. This indicates the importance of a rich pattern dictionary for the recognition of relational phrases in the relation linking task. We also investigate the mention detection task and the entity disambiguation task separately. The results indicates the importance of the mention detection task, which is the major reason to affect the performance of the end-to-end linking task. We have also conducted an efficiency evaluation towards different systems and different settings of TENET. The running time of TENET is roughly linear to the amount of data processed. This proves the scalability of TENET. And finally, we conclude our talk with a summary. We studied the problem of joint entity and relation linking with coherence relaxations, and the input of the problem is documents and target KB, and our goal is to select an optimal set of mentions which best describe the semantic meaning of the documents, with each of the mentions linked to an optimal concept in the KB. So we propose TENET as a solution which formulates a minimum cost rooted tree cover problem based on the knowledge coherence graph construct based on the document context and incorporates mention selection into the end-to-end joint entity and relation linking task. So that's the end of today's talk. Thank you very much for your attention, and I'm open to any questions. Thank you.